So a soap bubble looks like this. Here's part of it. Looks like this. And what's in here? Air. What's in here? And here it's like water or soap. Something, some index of refraction larger than air, right? Something. And it has a thickness. The soap bubble has a certain thickness. It's not very thick, but it's some thickness. It's a thin film. So the first ray comes here, and then it will reflect. Okay. So ray 1, will it experience a phase shift or no? This first ray comes in.
Yes.
Reflects. Yes, because
Index is higher.
good. Index is higher, so it's as if it traveled an extra half wavelength, didn't it? Let's look at the second ray. Second ray will travel a distance. Let's call it t, right? And then t back, and now it's ready to meet this one, right? Very fair. Will it experience a phase shift? Great. Okay. Great. No phase shift, but it went a distance twice, 2t, right? 2t. But did it go 2t in air or in the soap bubble? Soap bubble. What did we know? What happens to the wavelength when it travels? The wavelength, what happens to it?
Increases.
You mean decreases? Wavelength. Wavelength will be this. Lambda inside the material of index of refraction n is equal to lambda in vacuum or air, air divided by n. So you're able to squeeze in more wavelengths in here. Okay, more wavelengths. We used this fact when we did lenses, and we said basically the length is amplified. In fact, we did something in the worksheet yesterday, if I'm not mistaken, where we said a length L is actually gets inflated by a factor of n. Do you remember this from yesterday?
So it was on the quiz too.
It was on the quiz
I
today?
think I got it wrong.
I don't remember. So it gets inflated by a factor n. That's what I want to say. There is a factor. So yes, it travels, the actual thickness, if you measure it, it is t, but because it has a higher index of refraction, it's inflated by a factor n. So the difference in path is this minus this, right? So the difference in path, delta r, is 2 nt minus lambda over 2. And then we need to figure out what m's are, what m's to use. So if I want constructive interference, what do I do? For constructive, what do I need this to be? I need this to be a multiple of lambda, right? A multiple of lambda. Yes? Okay. I need it to become a multiple of lambda, and so I need, or if you like, 2 pi r over lambda equals to m something, right? M times 2 pi. So if you cancel the 2 pi's, we get this. For constructive, I need delta r, which is equal to this 2 nt minus lambda over 2 to equal to a multiple of lambda. So we get the following. So we get 2 nt to equal to m. M plus 1. No, not m plus 1. M plus a half, right? Yeah, plus a half. Thank you. Times lambda. I think I got it. M plus a half times lambda. And so t is equal to multiple. So you get m plus a half times lambda over 2n. Now, what should m be? Can m be, let's say, -1? No, right? Because -1 plus a half is minus a half, right? And so you get a negative number for the thickness you can't. So m can start at 0, right? If m is 0, no problem. Yeah, if m is 0, there is no problem. So the thickness is still not negative. Does that make sense? So then I can multiply that 2m plus 1 times lambda over 4n, and then m is equal to 0, 1. Okay, let me see here. For constructive, yeah, looks good. Let's look destructive now, for destructive interference. I think you know the drill. What do? Delta R, which is this, equals to what? Delta R. Yeah, which is 2n t minus lambda over 2 is equal to m plus 1/2 times lambda, right? And then you get 2n t is equal to if you move this to the other side, you get this m plus you get m lambda plus yeah, half lambda plus half lambda is lambda. Yeah, so lambda, right? Yeah, like that. So then I get 2n t is equal to m plus 1 times lambda, right? M plus 1 times lambda. In fact, so what can m be? It could be 0. Can it be -1? Why not? If m is -1, you get the thickness to be 0. Can the thickness be as thin as we like it? Yes, the thickness could be as thin as we like it. Let me do this. Let me call this one here. So instead of starting m at -1, I'm going to do this, okay? So I'm going to name this m prime, m prime, m prime, and then m prime plus 1 is m. I'm going to rename that as m. So I have that. 2n t is equal to m times lambda, and now m is equal to 0 or 1. Okay. Instead of having this starting at -1 and adding 1 to it, why not just get rid of the 1 and just start it at 0? Okay. And I think I have it, let me see here. Yeah, that looks good. So that means if I solve for thickness, I get m lambda over 2n. That's the thickness. Okay. So for if a wavelength happens to be 2nt divided by some number, then it will be, that wavelength will get cancelled. It will be destructive. We experience destructive interference. So that is that for the for these guys. Let me ask any questions on this thin film stuff. We might do a few more examples next week. And I have in mind some examples on double slits. Other than that, I think I have one more little topic to cover, and then one little topic to cover, and then so within an hour next week we'll start diffraction.
So are soap bubbles just like the opposite of an air wedge? Because they flip around.
Yeah. So instead of going all the interference going in air, for these, the interference is happening from the soap bubble. You know, that one, the first ray didn't experience a phase shift, right? Yeah, only the second ray. But this one, the first ray experiences the phase shift, and then the second ray doesn't.
Maybe I'm just still not understanding that last part there, but does that mean that the thickness of the soap bubble can be 0?
Then you have no soap bubble, right? If it's, but it's just saying it could be as thin as you like it to be.
Okay.
Yeah, it's just taking that mathematical limit, right? Because technically, even at the air wedge, at the point of contact, if it's truly there is no gap, then basically they're welded, right? But there is always a very close to 0 gap, right? Because then, if you think, if they're in contact, why is there air to be begun with between them, right? But then, if there is no gap at all, then they're the same piece of glass. So there has to be a little bit infinitesimal, very small. Okay. You probably experienced this when you did in mechanics, when you have an object like in when you did Archimedes' principle in water. If it's at the bottom, it will experience a buoyant force, right, from the bottom. But if it's at the bottom and there is no water, yeah. So, but if it's truly in contact, it will be like there will only be pressure from the top. It's like suction, right? When you have something that it will just be pressure on it, nothing from below. But there is always a little bit. Yeah. Okay. Let me pause this.